Hello, welcome to Flipped. So today we are on reactivity series, and the reactivity series really just compare relative reactivity of metals with each other. For example, potassium, sodium, calcium, etc. Okay, so this is potassium. Okay, is the most reactive. Okay, and down the series, okay, gold is the least reactive. Okay, so there's an easy way to remember this. Okay, it's called we have a mnemonic here, which is please stop calling me a colored zebra. I think leaders have cool silver glasses. This is corresponding to each of the metals here. So please is potassium, stop is sodium, calcium is calling, magnesium is me, etc. Okay, you have to note that this is the name of the metal. We are not using the chemical name, chemical symbol, because potassium is K. Okay, whereas the mnemonic, okay, starts with P and not K. So please take note that this is the name of the metal and not the element symbol. Now we'll start off with the first reaction using this series. Okay, this is a bit cramped. Okay, hope you will understand. First one, okay, you can see that the reaction with water. Okay, water, we are talking about steam and cold water. And it is easier to react with hot water than with cold water, because hot water provides additional energy from the heat, so that reactions can go faster. It's easier to react. Okay, so in some sense, cold water is the hard reaction. Okay, it's a very hard reaction to conduct, and only certain metals can react with cold water because it's not so reactive as compared to steam, which is hot water. Okay, and that's why I've written here. More reactive metals can react with cold water, whereas less reactive metals can only react with steam, which is hot water. And more reactive metals will form hydroxides, whereas less reactive ones will form oxides. Okay, let's take a look at the overall equation, which is metal plus water, okay, giving us metal hydroxide or metal oxide with hydrogen gas. Okay, this is the same, you will get this two products, okay, regardless of what metals you're using, just that the molar ratio will be different. Okay, let's go through one by one. In the case of potassium, okay, you can see that it's 2 units of it with 2 units of water, giving us a KOH, which is potassium hydroxide, okay, and hydrogen gas. It's an explosive reaction. Okay, means when you drop the metal in the water, it just explodes immediately. Whereas for sodium, okay, so you can see that how do we distinguish cold water and steam? Just look at the element symbol. You can see that all these are liquid. When it starts from here, okay, from zinc, it starts to become gas. Okay, and gas is steam, whereas liquid is cold water. Okay, so continue where we left off. Sodium has the same molar ratio as potassium. Okay, just gives you sodium hydroxide with hydrogen gas. It's a vigorous reaction. Calcium, okay, it has different molar symbols now. Please note there's only 1 unit of calcium. Okay, but still gives you calcium hydroxide, okay, with hydrogen. This is a normal speed, means it's just a normal reaction. It's not explosive, or it's neither is it too slow. Magnesium, okay, has the same molar ratio as calcium, okay. It forms magnesium hydroxide, okay, but it's a slow reaction now, okay, means it's slower than calcium. Next one is aluminium. Aluminium is it has its own molar ratio, molar quantity, okay. It forms aluminium oxide, okay, and it's a slow reaction. I put a star here because I want to explain it further. Because aluminium oxide, okay, when it forms, it stops the reaction completely, because this is a coating, okay, this layer, okay, for example, I have aluminium here, okay, when I drop it in water, okay, let me just draw my water. Okay, this is my water, right? Now it's in water. Okay, this is just the pure metal, aluminium metal. But when it in contact with water, okay, it forms aluminium oxide, and this is a layer that surrounds the remaining aluminium metal. Okay, and now this cannot react. Okay, and that's why this reaction is slow, and it will eventually stop after a while, because when you form this aluminium oxide, reaction cannot continue anymore. Okay, and that's why it's slow reaction with a special asterisk here. Okay, so all these metals, okay, above this line, okay, they react with cold water, okay, because they do not need the extra energy from the heat, okay, from the hot water, okay, to carry on the reaction. Okay, they do fine with cold water. Okay, then you can see that carbon, I did not have any reaction because carbon, okay, is in the list, but it's not a metal. It's just a place for it to be, to let us know the relative reactivity of carbon compared to the whole series. Neither is hydrogen. Okay, hydrogen is also not a metal, and that's why it doesn't have any reaction. It's also in here just to let us know an idea of how reactive it is compared with the rest. Okay, we will use both of them later in the reduction of metal oxides. Okay, so there's no reaction for both of them. And this is a very special element. Okay, it's called tin. Okay, there's no reaction. Okay, in some sense there's a reaction, of course, because it's between two metals that have reaction, right? So it obviously has to have reaction. But this one you don't have to know for your series or your O-level syllabus. You just have to know that it sits between iron and lead. Okay, that's all. Okay, and for whatever that's below hydrogen, okay, copper, silver, gold, they do not have any reaction with water or steam. Okay, so this summarizes the reaction with water, be it cold water or steam. Okay, let's move on. So now reaction with dilute acid. Okay, usually we use hydrochloric acid as an example. Okay, more reactive metals will react very quickly. Less reactive metals react slowly. Okay, this is quite intuitive. Okay, this is the reaction. Metal plus acid gives us salt and hydrogen gas. Okay, let's decipher this. So potassium, okay, using the potassium metal with hydrochloric acid gives us potassium chloride with hydrogen gas. Okay, you can see that all this dot. Okay, this one means it's the same as the previous one. Okay, in terms of the quantity needed. So 2Na plus 2HCl, okay, give us NaCl, sodium chloride with hydrogen also. Ca plus 2HCl give us CaCl2, calcium chloride with H2, hydrogen. Mg give us with 2HCl give us MgCl2 with H2, hydrogen. Okay, and aluminium, okay, is always the weird one. Okay, it always has its own reaction. Okay, reacts with 6 units of hydrochloric acid now to give us aluminium chloride. Okay, 2 units of it with 3 units of hydrogen gas. Okay, and as usual, carbon, tin, and hydrogen, we don't have reactions for them. We just leave it blank. Now we move on to zinc. Okay, zinc has 1 unit of zinc metal, 2 units of hydrochloric acid to give us 1 unit of zinc chloride with 1 unit of hydrogen gas. Similar for Fe, which is iron. Okay, follows the same ratio. Okay, and that's why I just write a dot here. And lead, okay, follows the same ratio as zinc as well. So this is 2 hydrochloric acid to give us lead chloride with hydrogen gas. Okay, and as usual, okay, copper, silver, and gold do not have reaction with dilute acids. Okay, let's look at how fast or slow the reaction is. So you can see that, okay, potassium and sodium, okay, it reacts explosively. Okay, calcium is just vigorous, means it's fast. Okay, it's faster than fast. Okay, but it's not explosive. Okay, whereas magnesium is just fast, whereas aluminium and zinc is normal reaction. Okay, normal speed, and iron, okay, and lead reacts very slowly. Okay, means it's just you have to wait very long for the reaction to complete. Okay, and that is all for reaction with dilute acid. Now we'll talk about the reduction of metal oxide. This is where it makes sense to put calcium and hydrogen in the reactivity series. Okay, let me explain why. Because carbon, okay, they can reduce metal oxides of metal below it. Okay, this is a bit confusing. Okay, the phrase here. Basically, what do I mean? Okay, metal oxide of metal. So for example, I have a magnesium oxide. So the metal is magnesium. Okay, understand? So basically, what I'm trying to say is that, okay, okay, this is not correct. Okay, maybe I shouldn't write this. Let me just change this. So sorry about it. Because magnesium is not below carbon. Okay, what's below carbon is, for example, zinc. So zinc oxide and zinc metal. Okay, so what I'm trying to say is that if this metal, for example zinc, is below carbon, okay, carbon can reduce its metal oxide. Okay, let me repeat that. if the metal, for example zinc, okay, is below carbon in the series, okay, carbon is able to reduce the oxide of zinc and not zinc itself. Okay, hopefully that's clear. So you can see from this equation here, let me just replace it with a zinc oxide instead. Then you'll be able to understand better. Okay, let me just change everything to zinc with carbon monoxide. Okay, so you can see that everything below carbon, okay, that means zinc, iron, all the way to go, okay, carbon has higher power, okay, it has higher reduction power. So you can reduce all these people here, all these metals here, okay, excluding hydrogen of course, okay, because it's not a metal. So you can see that zinc is below carbon, yes, okay, so if I sub in the equation here, zinc oxide plus carbon, okay, gives us zinc metal now, just a pure zinc metal with carbon monoxide. Okay, basically the metal of the metal oxide. Okay, whereas for hydrogen, okay, it can reduce metal oxides of metal below it. So this is hydrogen, it can reduce copper oxide, silver oxide, gold oxide. Okay, anything that's below hydrogen. Okay, then if so you can ask me, what about all these metals, metal oxide, sorry. Okay, all these are above carbon and hydrogen, right? So what can I do with them? Okay, what you can do is electrolysis, which we will be talking about in a separate video. Okay, it's a standalone chapter of itself, electrolysis. Okay, let me just recap this concept here. Basically, whatever's below carbon, okay, zinc, iron, tin, lead, copper, silver, gold, their oxides can be reduced with carbon. Not them as a metal, but their oxides. Okay, for hydrogen can reduce copper, silver, and gold oxide, and not copper, silver, gold metal. Okay, hopefully that's clear. You cannot reduce a metal. You can only reduce a metal oxide. Okay, so you just follow the reactivity series. Okay, based on what position they are. Okay, next we'll move on to displacement reactions of metal. So basically, more reactive metals, they lose electrons to form positive ions more easily. Okay, this reaction is as such. Okay, basically, this is my sodium solid. Okay, it forms sodium plus and electron. Okay, compare this with gold. Okay, Au to give us gold plus and electron. Okay, this one, the first potassium, okay, sorry, sodium, okay, it will form its positive ions and electron much more easier than gold. Okay, this is what we mean. More reactive metals, they lose electrons to form positive ions more easily. Okay, this is a greater tendency to oxidize. Okay, and this is also based on this reactivity table. Okay, as usual, okay, we will just ignore carbon and ignore hydrogen and ignore tin. Okay, tin, we leave it there, but we don't have to know the reactions. Okay, so let's take a look. So you can see that, for example, my reactivity of sodium is better than calcium. This is because sodium is here, calcium is here. Okay, so you can see that sodium is higher than calcium. And that's why sodium solid can displace calcium aqueous ions. Okay, so you can see that solid. Okay, so first of all, you have to know that the higher up can displace the bottom people, correct? And the condition is that a solid to displace an aqueous ion, and it's not solid to displace solid. Okay, that doesn't make sense, right? For two solid to react. So let's take a look at sodium and calcium. So sodium, I require 2 molar units of it, 2 sodium metal solid, reaction with, for example, calcium nitrate, okay, which is aqueous. Okay, so the conditions are met, solid and aqueous here. Okay, so they basically swap place. You can see that now my sodium takes over this nitrate, okay, to form sodium nitrate and kicks out the calcium. Okay, he's like, oh, because I'm more reactive than you, so you have to get out and let me take your place. Okay, that's basically what this reaction is. Okay, he kicks him out. Okay, and now calcium becomes a solid and sodium nitrate forms aqueous. Okay, this is a chemical reaction, chemical equation that we are familiar with. Now I'll introduce you to this thing called ionic equation, which is basically the same thing, except now you do not include the anions which remain the same charge. What do I mean? So you can see that nitrate here and nitrate here, they are both NO3 minus. Okay, they are the same left hand side and right hand side of the reaction. Means after the reaction they do not change. Okay, means I exclude them in my ionic equation. Okay, so in summary, ionic equation is just to exclude repeating ions, okay, on left and right hand side of the equation. So what remains here is just calcium 2 plus and Na2 plus, 2Na plus here, okay, for ionic equation. Now let's talk about magnesium and copper. Let's change color here. Magnesium is here, copper is all the way down here. So I can see that yes, magnesium is more reactive than copper because it occupies a higher position than copper. So therefore, magnesium solid can displace copper aqueous ions, no problem. Okay, in fact, it's done very easily because such a big gap, right? Whereas for sodium, calcium, maybe there's a bit difficulty because their reactivity is quite similar. But for magnesium and copper, is easily done, okay, because the difference in reactivity is so great. So this is similar to this, okay, basically, magnesium is like, okay, I want you to get out, okay, I want copper to get out, I want to take over its sulfate ions, okay, so basically, magnesium will just join with sulfate to form magnesium sulfate here, okay, and copper will be kicked out as a metal, as a solid here, okay, and similarly, ionic equation is basically to tell me that, oh, okay, sulfate is repeated on both sides, okay, SO4 2 minus. Okay, this is NO3 minus. Okay, so SO4 2 minus sulfate is repeated on left hand and right hand side. So I just exclude them in the ionic equation. Okay, so be careful. Chemical equation, you have to include everything. Ionic equation, you just have to include things that change. Okay, if the anion or positive ion, cation, doesn't change, you just exclude them. Okay, and so this one has a bit special because it has observation here. Okay, basically copper 2 plus, as we learned in the previous chapter, is a blue color solution. Okay, Mg2 plus being a group 2 metal, it's colorless. Okay, its solution is colorless, and copper solid is pink. So what will we observe when this reaction takes place is that the original blue solution, okay, upon the reaction finishing, will become a colorless solution. Okay, and a pink solid will form because this one do not dissolve in this magnesium sulfate solution. Okay, so it forms its own pink solution. So if I were to draw it out, okay, for you to see easier, okay, this is my original beaker. Okay, when the reaction happens, what happens is this. Okay, this blue solution decolorizes to this colorless solution with a pink solid at the bottom. Okay, this is basically the reaction in picture. Okay, let's move on to the final part of this chapter, which is the decomposition of metal carbonates. So basically, I'm still using this table, okay? So this whole chapter just revolves around this reactivity series. Okay, I can exclude the first two immediately because sodium carbonate and potassium carbonate are very stable to heat. Okay, they will not decompose. What do I mean? This is my sodium sulfate or potassium sulfate. When I burn them, okay, I subject them to fire, okay, they will not change. Okay, they will just remain solid. Okay, because they are so strong. Okay, they are very thermally stable. Okay, they will not decompose. Whereas the rest of the metal carbonates will decompose. So please take note that I'm talking about carbonates here. I'm not talking about the metal themselves. Okay, metal themselves, if you heat them up, they can decompose. But I'm talking about the metal carbonates. For example, zinc carbonate, potassium carbonate, sodium carbonate, etc. Okay, I'm not talking about the metals themselves, but I'm talking about the metal carbonates. Okay, yep, so back to this. This is a reaction that will take place. This is the metal carbonate, solid. It will be decomposed into metal oxide, solid, with carbon dioxide gas coming out of it. So let's take a look. In this, an example I have here is zinc. So zinc is here. Okay, yes, it's part of the group that is able to decompose. Okay, this group, everybody can decompose except for potassium and sodium. Okay, so zinc can decompose, yes. Zinc carbonate can decompose. So I just write zinc carbonate here, decompose to zinc oxide plus carbon dioxide. Okay, it's quite simple. Okay, you can replace this with whichever metal that is in here. Okay, calcium to gold. So last point to take note is that stability, okay, thermal stability decreases down the reactivity table. What do I mean? So potassium and sodium, I just take it out, okay? Let's just leave it out for discussion. So calcium, let's start with calcium. Calcium is still quite thermally stable, but it can decompose after a while. Okay, so I'm saying that calcium carbonate is the hardest to decompose because it's still quite thermally stable. Okay, whereas if I go all the way down to gold, okay, now it's a different story. Okay, it's very not thermally stable. Okay, means the moment I expose the for example gold carbonate to heat, it will just decompose, okay, to metal, to gold oxide, for example. Okay, because thermal stability decreases down the group, okay, and hence down the group it's easier to decompose. Hopefully that makes sense. Okay, and that is all for the reactivity table.